Hello PCH. So this video might be a little long, so you might want to chunk it and do maybe a page at a time. It's up to you, depends on how busy you are. We're going to cross over several topics, and it's all going to be kind of brand new, so feel free to play this over several times. The first thing we're going to talk about or introduce is something called the dot product, aka also known as scalar product, because the result is always a scalar, or inner product, which you will discover why in a little bit. Okay? Me being me, I have put up online in our locker the derivation of the dot product. It's way too long to do here in the video, but for any of you math fellow nerds out there like me who like to see those derivations, I did work it out and put it up online for you. Okay, so let's start off. What is the dot product? What we are first looking at is the definition. There's going to be two ways to find the dot product, but the actual definition, and again you would read this A dot B, not A times B, A dot B, is the product of the magnitudes of two vectors times the cosine of the angle between them. So remember, the absolute value means magnitude, so we have a little diagram here. One of the uses of the dot product is to find the angle between two given vectors that are tail to tail. So in this particular definition, I would use the dot product when you are given the magnitudes and the angle between two vectors. Later on, we will have a different method when the information comes to you in a different format. So here we want to find the dot product. So we have A dot B, again, is going to be the magnitude of A times the magnitude of B times the cosine of 40 degrees. And when we work that out, you get about 26.812. So notice that we have here an acute angle, and because the cosine of an angle less than 90 is going to be positive, whenever your angle is acute, you will always get a nice positive answer. Then over here, A dot B, so here's A dot B, is going to be the product of their magnitude times the cosine of the included angle. Well, we know that cosine in the second quadrant is negative, so it makes sense that if you happen to have an obtuse angle, then your dot product is going to be a negative number. All right, that's really, calculation-wise, that's pretty straightforward. So we have here, whether it's acute, you will have a positive dot product, and when it is obtuse, you will have a negative dot product. So what do you think would happen, or what would theta have to be for the dot product to equal 0? It's kind of like asking cosine of what degree equals 0, and the answer to that is going to be when theta is 90-degree angle. That is really helpful. As you go forward with these, there's a lot of physics involved in this, but when you have two vectors that are perpendicular, there's going to be three different words we're going to get for that. We're going to get orthogonal and we're going to get normal. Those both mean the same thing, that the vectors are perpendicular to each other, and that is going to come in handy as we move forward. And so the dot product, because it has built in the cosine of an angle between two vectors, is a useful way of finding out whether two vectors are orthogonal, acute, or obtuse, or what the actual angle is. So let's look at a few of these. we have case 1 where theta equals 0 degrees. So these two vectors are going in the same direction. It's kind of like two forces working together. In that case, the dot product is going to be 5 times 7 times the cosine of 0, which remember is 1. So the idea behind that is you have two forces that are working together, so it gives you an even stronger force. Here we have a dot product given the angles are going, the vectors, sorry, are going in opposite directions. So this would be 5 times 7 times the cosine of 180. And since cosine of 180 is a -1, we get a -35. Oh no, I hit something.
According to wikipedia.org.
Sorry, I hit something on my computer. Okay, then case 3. Here's our orthogonal. I'm going to just start to introduce these words because they're going to come up more. Orthogonal, normal, perpendicular. 3 different ways to say the same thing. So if you want to sound impressive and have someone not really know what you're talking about, you can say 2 things are orthogonal. So the dot product, notice, would be 5 times 7 times the cosine of 90 degrees, which is 0. All right, so there's our orthogonal. This is going to be important as we move forward, that the dot product is always a scalar. Later on, you're going to get what we call the cross product, which is going to be a vector. But in this case, it's a scalar, which is why we also call it the scalar product. Okay, so let's look at the other way we can calculate the dot product. So on the previous page, we got the definition of the dot product, which is the product of the magnitudes times the cosine of the angle between them. That's your definition. One of the uses of the dot product is to find an unknown angle. But sometimes, and again, that method is great when you are given the magnitudes and you're given that angle between them. But sometimes, as we have seen, you are given vectors in component form in terms of a scalar times their x, y, z components. What is nice about this is you've actually already done this. So if I have a vector A in component form, so xi times I plus y1 times j plus z1 times k, so that's our vector A, and then we have here our vector B. Well, remember when you multiplied 2 matrices and you did a row times a column, and you were doing basically a dot product. You were multiplying the same positioned elements and then adding the result together. It's exactly what you do when you are finding a dot product. And again, this is not the definition, it's just another way to do it, and it is going to lead to the reason why we call this the inner product. I'm going to introduce the reason behind that in a bit. So you take x1 times x2, and then you take y1 times y2, then you take z1 times z2, and that is your result. Okay? Again, notice the result will be a scalar because it is still the dot product, and the dot product always gives you a scalar. So let's do one. We have here C and D, and so if I'm going to find their dot product, since they came to me in component form, it'll be 4 times 2 plus -6 times 5 plus 9 times a -3. So 8 minus 30 minus 27 results in -49. Again, notice the result is a scalar. All right, that was nice. Now, let's find the angle between those two vectors, because those are in component form. So we're going to use the definition, and we're going to isolate cosine theta. So I have that definition up above, and I can then take, so notice that now in the numerator is the dot product divided by the product of the magnitudes. Awesome. Okay, well, we have already found our dot product in component form, so I know that my numerator will be a -49, and off to the side we are going to find the magnitude of our individual vectors. So we know that, oops, not A, silly me. In this case, it is C. Oh, one more. Okay, so the magnitude of C, and I'm just going to let you, I don't know, I don't want to confuse you, so let me rewrite this in terms of C's and D's. Hopefully that makes sense. It doesn't want to erase. Okay, you're going to have to deal. Why is it not erasing? There we go. Now it's erasing. I just want to write it in terms of the letters we're actually using. So the dot product of C and D divided by the magnitude of C times D. There we go. All right, so we have negative 49. We need to find the magnitude of C. Again, that's just Pythagorean theorem. So 4 squared plus 6 squared plus 9 squared, and it's going to be square root of 133. And then we find the magnitude of D. It is going to be 2 squared plus 5 squared plus 3 squared, and that gives us 425, 9. It's going to add up to 38. I'm not that fast, I just have already figured out these numbers. So on the bottom here, we have multiplied by the square root of 133 times the square root of 38. And that gives us the cosine of theta, which is going to be a negative 0.689. So right now, I should ask you, is theta going to be acute or obtuse? And you should give me back an answer that says it will be obtuse, because theta is going to equal the inverse cosine of negative 0.689, which is going to give us around 134 degrees. Okay, so that is one of the applications of the dot product, to find the angle. And how you find the dot product doesn't really matter, but you can, whether it's component form or whether it came to you tail to tail, doesn't matter. You can still isolate cosine and find that angle. All right, let's do another example. Find the dot product and the angle between the vectors R and S, and they come to us in component form. So let's first find our dot product. That is going to be negative 8 times 6. I will write it out. 4 times a negative 4, and 1 times 5. So that gives us the lovely number of negative 59. That's our dot product, which right off the bat tells you we know the angle between them will be obtuse. But we are also going to want to find the magnitude of each of these, since we're going to keep continuing and find cosine of the angle between them. So this will be 64 plus 16 plus 1, which gives me, 81. Square root of 81 is 9. That was nice. Nice to have a friendly number for once. And this one will be 36 plus 16 plus 25. That all adds up to square root of 77. Not as interesting. So we know, we have our dot product done. Now we know that the cosine is going to be the dot product. I'm going to just, it's worth keep emphasizing, over the magnitude, product of the magnitudes. So this will be a negative 59 divided by 9 times the square root of 77. And so when we go to find theta, did I give myself, it'll be the inverse cosine. Negative 59 over 9 square root of 77 would give you a negative 0.747. So theta is going to approximately be 138 degrees. Okay? All right. This bottom part is kind of telling you why it's the inner product. We already saw why it's a scalar product, because the result is always a scalar. Why do we call it the inner product? Well, we know that the dot product of orthogonal perpendicular vectors is 0, since cosine of 90 is 0. And if you look at your ijk vectors, it doesn't always look like it, but all of these unit vectors should be perpendicular to each other. So if I'm finding the dot product of different vectors, I know that I dotted with I is going to be 1. Why? Because you're dotting I with I. So it's 1 times 1 plus 0 times 0 plus 0 times 0. So you're going to get 1. If I were to do, let's stick with I here. I dotted with J, we know we'll get 0 because they're orthogonal. So the cosine of 90 be 0. I dotted with K, it's going to be 0. All right, that was nice. Now, what if I had J dotted with I? Again, perpendicular, 0. How about J dotted with J? Well, they're in the same direction. As we saw, cosine of 0 is 1, and the unit vectors each have a magnitude of 1. J dot K, also 0. They are perpendicular. So now let's do our K. We know that K dotted with I is going to be 0. We know that K dotted with J will be 0 because they are orthogonal. All right, here we go. Last page. Hope you're still with me. Let's start to look at the applications and the physics that go with vector and scalar projections, and what are they? What do they have to do with dot product? So a scalar projection is kind of like if you had, let's say, a lean-to or something, and you have the ground down here, and let's say it was raining. Well, a scalar projection is kind of like the shadow, the perpendicular shadow that gets created by this awning on the ground. So A, even though it's a vector, and later on it's going to represent, say, a force, is getting projected onto what we would call a displacement vector B, and that shadow, because it only falls perpendicularly, would stop here. And we're going to start with looking at the scalar projection. So this P is not a vector yet. It will become one, but right now it's just going to be a scalar. All right, so what does this represent? And again, my physics is not very good. I took it in college, physics for non-majors from a Nobel laureate. Not a lot of math, but it was a lot of interesting demonstrations. I was a philosophy and English major, didn't get math degree till later, so sorry for this. Some of you, your physics is probably way sharper than mine, but I will do my best just to give you a little idea of what we're doing. Let's say this was a box. I'm going to make it small because I don't want it too much in my picture. And here you are with your arms and your legs and your very long body. And the vector A is, let's say, a rope that you're pulling so that you can move your box forward. Well, the force that you are pulling that box is going to be affected by the direction that you are moving and the angle at which you are pulling that rope in. So they are both kind of related to each other. And again, this is what you would look at in a physics application. But let's talk a little bit about the math behind this before we get too much into the applications. So a scalar projection is basically, we're going to start off with just its right triangle trig. That's really all it is. We know that the cosine of that angle is the adjacent, which is just P as a scalar, over the hypotenuse as a scalar would be the magnitude of A. And if I then isolate my P, notice I get what we would call a scalar projection. It's really just right triangle trig. And if theta is acute, then the scalar projection is going to equal whatever the magnitude of P is So it'll just equal, and we then drop the magnitude and the stuff, and we just call it P. It's just a lot easier. But if theta were obtuse, so let's say A was coming out here, and this was theta, then if you drop a line perpendicular, notice that the scalar projection is going to be the opposite of P, because it's going in the opposite direction of our displacement vector. B is called the displacement vector, A would be like your force vector, and again, it's going to affect how fast and how much force you use to move that box. All right, that's kind of just the background. So we know that scalar projection is just isolating the adjacent side in right triangle trig. What does that have to do with dot product? Well, I'm so glad you asked. So let's look at how we get the dot product into this. So we start off with P equals the magnitude of A times cosine theta. Again, that's just the adjacent equals the hypotenuse times cosine theta. That's really all it is. So as I'm doing these derivations of the other forms for scalar and vector projection, I want you to remember you don't have to memorize every single version, because the derivation really is pretty straightforward. So what I'm going to do is I want to turn this into a dot product. We're going to multiply by a very fancy form of 1. Basically the magnitude of our displacement vector over itself, because that equals 1. What I can then do is rearrange my terms. Here's A, here's B, here's cosine theta, all over the magnitude of B, and hopefully you recognize in the numerator that is the definition of a dot product. So that's why we get, here's A dot B over the magnitude of the B. Notice that you're always dividing by the magnitude of the displacement vector, what you are projecting onto. All right, so that is another form. You're going to get many different forms of these. I'm not sure what I just did. I did something weird. So we have this form, and now we have this form. All right, now that's still, in both cases, a scalar. And what we really want is a vector projection, because that's force is always about vectors. So how do we turn this into another form, into a vector? Well, here we have this scalar projection. So remember that that's just going to be a scalar. And I am multiplying it by, do you recognize what that is? Vector B over the magnitude of vector B. That is a unit vector. It's a unit vector in the direction of our displacement vector. So remember, you have a scalar. You're multiplying it by a unit vector, which means you're not changing its magnitude because you're multiplying by 1, but you are making sure that it's going in the direction of B because it is the unit vector B. So how does this then all come about? Well, we have from above, so this is really bringing this down, we had that P equals, so it's another form of this, the dot product over the magnitude of B, and if I multiply that by my unit vector, which is the vector B over the magnitude of B, you get this big ugly mess. I know, it looks like a big ugly mess, but this is really what we have, because all of this is just a scalar. It's just a number. So the final result is that now I have to put an arrow over this because this is now our vector projection, is the dot product of the force with the displacement over the magnitude of the displacement vector squared times, that's not a dot product, that's now an actual times because the dot is there, the vector B. That's what turns it into a vector. By doing it by the unit vector, you're not changing the magnitude of that. So there is our result that we just represented. Many different forms. So again, it all depends on how the information comes to you as to which one might be the best to use. So I think this is a good place for us to then do a couple examples where the information comes to us in different forms. So here, the first example, we've got vector B in its component forms. We are given A is, and again, we're going to keep B as our displacement vector. A is like our force vector. We're given its magnitude, and we are given the angle between A and B. So if I were to, I'm not going to do B in a three-dimensional system, but just to kind of give you a little picture of what we're looking at here. So here's A, here is B, there's A, there's B. We're looking for both the scalar and vector projection of A onto B. So initially we're going to do the scalar projection, which when it comes to you in this form is really easy, because remember that's just A times the cosine. In this case that was 70 degrees of 70 degrees. It's really nice when they give you the magnitude. So this is 10 times cosine of 70. So as a scalar projection, that is going to equal 3.42. So that would be the length of this. Now we want to turn that into a vector that still has a magnitude of 3.42, but is going in the direction of B. In order for us to do that, we need to know what was the magnitude of B, because we are going to use the relationship that the vector projection is going to be the dot product, or well, in this case we can use our A cosine theta, whatever that result was. We're going back up to we're going to take the scalar. I'm doing this one right here, because this is what turns it into a vector. So let me erase that little dot. I don't like it. Okay, so the vector projection is going to take the scalar projection, 3.42, and we're going to multiply by the magnitude of B, divide by the magnitude of B, and then multiply that against, because that's our unit vector. That turns it into a vector in the direction of B. So off to the side here, let's find our magnitude of B. So again, remember, magnitude is just Pythagorean theorem, 64, not 64 squared, just 64 plus 25 plus 9. So this gives me 3.42 divided by, what do I have here? I've already simplified it, so I guess that's 98, square root of 98, 7 rad 2, times the vector B, which is 8, negative 5, 3. So notice what we're doing is we're just multiplying by a scalar, and this will give us our vector projection. So when we do that, in the end, you're going to get 2.76, because it is a vector now. It's no longer a scalar, so it has to have x, y, and z components, and that would be it. So you have a scalar projection, which is again a scalar. It's just the length of p. When we turn it into a vector, it then has magnitude and direction, and there it is. Okay, now that was given, it was nice. Our force was given to us as a magnitude. We knew that angle between them. B was in component form. That's fine. What happens if both our vectors, both our force and our projection vector, come to us in component form? So again, how do I know which one is which? Well, we are doing the projection of R onto S. So what that tells me is that S is the vector down here, R is going to be this vector, and so we are going to find first the scalar projection and then turn that scalar into a vector. Since I'm given it in component form, we are going to use the version, and again we just want to do the scalar first. So this is going to be r dotted with s, the dot product, over the magnitude of your displacement vector. Everything there is just a number. So r dotted with s is going to be 1 times 5 plus 4 times a negative 2 is a negative 8, I believe. And then negative 7 times a negative 3 is a positive 21. That's all going to get divided by the magnitude of s, 25, plus 4, plus 9. And so in the end, that is going to give me 18 over the square root of 38. All right, that is our scalar projection. So notice the difference. Above, when I knew the magnitude, I could just do the right triangle trig, basically. The hypotenuse times the cosine of the angle, that gives you your scalar. If you have the component form, then you do the dot product divided by the magnitude of your displacement vector. That is our scalar projection. We now want to turn that into our vector projection. So turning P into P as a vector means I'm taking the scalar projection, which was this, and multiplying it by the unit vector of S. So remember, that's going to be S over the magnitude of S, which is this. So we are going to have 18 over 38, because it gets rid of your square root, which is kind of nice, getting multiplied by 5, negative 2, negative 3. That's going to give us our vector projection. And what I like to do, if I'm going to do it without decimals, I'm going to reduce this. That's 9 over 19. And so my end result, what am I doing? When I multiply them together, I'm trying to be fancy with colors here, sorry. Just cut to the chase, right? All right, so that's going to give me 9 times 5 is 45 over 19. 9 times negative 2, negative 18 over 19. And then lastly, we have 9 times negative 3, negative 27 over 19. So that is a vector that is the length of whatever 18 over square root of 38 is, but going in the direction of S. Okay? That's pretty heavy. So you might want to break it down, maybe watch this again. We will be doing more with it in the coming days though.